History of Jupiter, the Colossus of our solar system. Let's continue our documentary series dedicated to the planets of the solar system, with the goal of comprehensively describing their history and characteristics. After exploring the scorching plains of Venus, the red deserts of Mars, and the torrid little world of Mercury, it's time to leave the inner rocky planets behind and turn our gaze toward the first of the giants, Jupiter, the Colossus of our solar system, so massive that its gravity influences the entire planetary equilibrium. In this new chapter, we won't limit ourselves to describing the best-known features of this imposing planet. Instead, we'll go beyond, exploring its complex atmospheric structure with the iconic Great Red Spot, its extremely powerful magnetic field, its fascinating ring system, and the surprising entourage of moons that accompany it, some of which might harbor subsurface oceans. Comprehensive means exactly this: a detailed account rich with information and insights that will lead you to look at Jupiter with new eyes, appreciating its complexity and hidden charm. Jupiter is a planet of contrasts and decidedly surprising characteristics. The fifth world of our solar system, so massive that it alone contains more than twice the mass of all other planets combined, so large that it could contain over 1,300 Earths within its volume, yet so rapid in its rotation that it completes a turn on its axis in less than 10 hours. So imposing that it creates a magnetic field 14 times stronger than Earth's, but lacking a solid surface to walk on. Its atmosphere, a whirlwind of colored bands and cyclopean storms, hides a world whose composition mirrors the primordial nebula from which the entire solar system was born, a living archive of cosmic origins just waiting to be deciphered. But let's proceed in order and get to know this planet better through its numbers. With an equatorial diameter of 142,984 kilometers, or 88,846 miles, about 11.2 times that of Earth, Jupiter is the largest planet in the solar system. Its mass is approximately 318 times that of Earth, representing 71% of the total planetary mass in the solar system. Despite its imposing dimensions, its density is surprisingly low, 1.33 grams per cubic centimeter, 82.9 pounds per cubic foot, less than a quarter of Earth's, as it is composed primarily of light elements like hydrogen and helium. Jupiter orbits the Sun at an average distance of 778 million kilometers, or 484 million miles, or 5.2 astronomical units, completing a revolution in 11.86 Earth years. Its orbit is relatively a little eccentric, with a value of 0.048, causing its distance from the Sun to vary less than many other planets. The gas giant rotates on its axis in just 9 hours and 56 minutes at the equator. The deep internal rotation is slightly different, about 9 hours and 50 minutes, making it the planet with the fastest rotation in the solar system. This rapid rotation causes a notable polar flattening, with a polar diameter almost 9,300 kilometers, or 5,780 miles, less than the equatorial one. The axial tilt is minimal, only 3.13 degrees, which means Jupiter doesn't experience significant seasons. The temperature in the upper part of the clouds is about minus 145 degrees Celsius, or minus 230 degrees Fahrenheit, while pressure and heat increase dramatically going deeper. The surface gravity, measured at the level of visible clouds, is 2.4 times that of Earth. If you weigh 70 kilograms or 154 pounds on Earth, you would weigh 168 kilograms or 370 pounds on Jupiter. This cold, objective data doesn't tell the true story of this gas giant, however. Its biography is written in the complex patterns of its cloud bands and in its vortices that last for centuries. Lacking a solid surface and with an atmosphere that gradually fades towards a perhaps rocky core, Jupiter represents a type of world completely different from the inner rocky planets. Its clouds, organized in belts and zones of different colors that surround the planet parallel to the equator, are the visible result of powerful jet streams flowing in opposite directions at different latitudes, creating turbulent boundaries where vortices and storms form. The detailed study of Jupiter became possible only after the invention of the telescope, although the planet was known since antiquity as one of the wandering planets visible to the naked eye. Galileo Galilei in 1610 was the first to observe it with a telescope, discovering the four major Jovian moons, Io, Europa, Ganymede, and Callisto, now known as the Galilean moons. This discovery was revolutionary, providing one of the first observational proofs that not all celestial bodies orbited around Earth, thus supporting Copernicus's heliocentric model. Since then, Jupiter has continued to fascinate astronomers of every era. The Great Red Spot, perhaps Jupiter's most iconic feature, was first reliably observed by Italian astronomer Giovanni Cassini in 1665. It's an immense anticyclonic storm, large enough to contain 2 or 3 planets the size of Earth, that has been raging for at least 350 years, although in recent decades it has gradually reduced in size. Its reddish coloration is probably due to chemical compounds that are brought to the surface by upward currents and then altered by solar radiation. Jupiter's visible appearance is dominated by the alternation of light and dark bands running parallel to the equator. The light bands, called zones, are regions where gas rises upward in the atmosphere. The dark bands, called belts, are areas where the gas descends. This zonal aspect is the result of the planet's rapid rotation combined with the convective motions of the atmosphere and the Coriolis effect, which bends the ascending and descending currents in opposite directions in different latitude bands. Jupiter's atmospheric composition largely reflects that of the primordial solar nebula, being composed of approximately 89 to 90% molecular hydrogen and 10% helium, with traces of methane, ammonia, hydrogen sulfide, and water vapor. The visible colorations in the clouds are due to the photochemical compounds produced by the interaction between sunlight and these trace elements. In particular, sulfur and phosphorus compounds are responsible for the brownish and reddish tones, while crystallized ammonia forms the higher white clouds. Jupiter's internal structure still presents many mysteries, but current models suggest a layered organization. Below the visible cloud layer, the atmosphere becomes progressively denser until it transforms into an ocean of liquid hydrogen. About 10,000 kilometers below the clouds, the pressure is so high that hydrogen assumes a metallic liquid state, in which electrons are free to move, making hydrogen an electrical conductor like metals. This layer of metallic hydrogen in rapid rotation is believed to be responsible for Jupiter's extremely powerful magnetic field. At the center, probably there is a solid core composed of heavier elements, with an estimated mass between 7 and 25 times that of Earth. This magnetic field is the most powerful among all the planets in the solar system, about 14 times more intense than Earth's, and with a volume 20,000 times greater. Jupiter's magnetosphere is so vast that if it were visible from Earth, it would appear in the night sky as large as the full moon, despite the enormously greater distance. This gigantic magnetic bubble traps charged particles, creating intense radiation belts similar to Earth's Van Allen belts, but much more powerful. The radiation is so intense that it represents a serious danger for space probes approaching the planet, requiring special shielding to protect the onboard electronics. Another notable aspect is Jupiter's ring system, much less showy than Saturn's, but no less interesting. Discovered only in 1979 by the Voyager 1 probe, this system consists of 4 main components: the innermost and diffuse halo ring, the brighter main ring, and the 2 outer rings called gossamer, veil, associated with the moons Amalthea and Thebe. Unlike Saturn's rings, which are primarily composed of ice particles, Jupiter's are formed by tiny dust particles, probably material ejected from the small inner moons due to meteorite impacts. The close-up exploration of Jupiter has been a complex undertaking, given the enormous distance from Earth and the hostile environment surrounding the planet. The first probe to visit the gas giant was Pioneer 10 in 1973, followed by Pioneer 11 in 1974. These missions provided the first close-up images and direct measurements of the Jovian environment, also discovering the existence of radiation belts and rings. The Voyager 1 and 2 probes, launched in 1977, visited Jupiter in 1979 and shortly after, providing detailed images of the clouds and discovering volcanic activity on Io, the first observation of active volcanism outside of Earth. A qualitative leap in Jupiter's exploration came with the Galileo mission, launched in 1989, which reached Jupiter in December of 1995 and became the first spacecraft to orbit the planet. Before entering orbit, Galileo released an atmospheric probe that penetrated directly into the planet's atmosphere, transmitting data for almost an hour before being destroyed by pressure and heat. The mother probe continued to orbit Jupiter for almost 8 years, completing 35 orbits around the planet and conducting in-depth studies of the Galilean moons, including the detection of a probable ocean under Europa's icy surface. The mission deliberately concluded in September of 2003 when the probe was made to plunge into Jupiter's atmosphere to avoid possible contamination of potentially habitable moons in case of malfunction. Other probes that have provided data on Jupiter during close flybys include Cassini-Huygens in 2000, headed towards Saturn, and New Horizons in 2007, headed towards Pluto. Both took advantage of Jupiter's gravitational assist to accelerate towards their final destinations, simultaneously collecting data and images of the gas giant. Hey guys, just a moment before we continue. Be sure to join the Insane Curiosity channel. Click on the bell. You'll help us to make products of even higher quality. The most recent and technologically advanced mission is Juno, launched by NASA in 2011 and arriving in orbit around Jupiter in July of 2016. Specifically designed to study the composition, gravitational field, and magnetic field of the planet, Juno orbits on a highly elliptical polar trajectory that brings it to just 4,200 kilometers or 2,610 miles above the polar clouds every 43 days. This particular orbit allows the probe to avoid the zones of maximum radiation and to obtain a complete mapping of the gravitational structure, offering precious clues about the distribution of mass inside the planet. Its instruments, protected by a robust titanium case, include a magnetometer, a microwave spectrometer to study the deep atmospheric composition, an infrared spectrometer to analyze the upper atmosphere, and a visible light camera called JunoCam that has provided spectacular images of Jovian clouds seen from perspectives never observed before. The Juno mission required extraordinary engineering to face Jupiter's hostile environment. To withstand the intense radiation belts, the spacecraft's electronics are enclosed in a titanium vault, weighing 200 kilograms or 440 pounds, which provides shielding equivalent to that of a 9mm thick lead wall. The probe's solar panels are the largest ever used for a planetary mission, with a total surface area of 60 square meters or 645 square feet, necessary to capture the weak sunlight at that distance from the sun. Despite these precautions, NASA engineers had predicted that Jovian radiation would gradually degrade Juno's instruments, which is why the mission was initially planned to last only 20 months. Surprisingly, the probe has resisted much better than expected, allowing multiple mission extensions. The images sent by Juno show Jupiter's poles as we have never seen them before. A chaotic assembly of octagonal cyclones at the North Pole and pentagonal ones at the South Pole, which remain stable over time, defying our knowledge of fluid dynamics. The probe has also revealed that the atmospheric bands and the Great Red Spot extend much deeper than previously thought, and has provided data suggesting a diffuse rather than compact core. The analysis of the gravitational field has also allowed determining that the winds observed on the surface extend to depths of about 3,000 kilometers or 1,865 miles, involving about 1% of the planet's total mass. Initially scheduled to conclude in 2018, the Juno mission was extended until 2021 and then further until 2025, allowing more complete coverage of the planet and more detailed observations of the Galilean moons. The probe, at the end of its mission, will be deliberately made to plunge into Jupiter's atmosphere, like Galileo before it, to avoid biological contamination of Europa and other potentially habitable moons. Jupiter's moon system is a veritable miniature solar system with at least 79 confirmed satellites of various sizes. These satellites can be divided into different categories. The 4 large Galilean moons, Io, Europa, Ganymede, and Callisto, an inner group of 4 small moons, Metis, Adrastea, Almothea, and Thebe, that orbit inside Io's orbit, and numerous groups of irregular moons, probably asteroids captured by the planet's gravity at different times, which orbit at great distances with often eccentric and retrograde orbits. Most of these moons, interestingly, take their names from the lovers of Roman deities, thus creating a curious mythological connection. The 4 Galilean moons are the largest and most interesting, each with unique characteristics that make them worlds unto themselves, worthy of dedicated exploration. Ganymede, the largest, is also the largest moon in the entire solar system, with a diameter of 5,268 kilometers or 3,273 miles, even larger than Mercury. It's the only known moon to possess its own magnetic field, probably generated by a molten iron core. Its surface is divided into 2 types of terrain: dark, older, and heavily cratered regions, and lighter regions characterized by numerous parallel grooves, probably formed by tectonic processes. Like Europa, Ganymede is believed to hide a subsurface ocean, located at a greater depth and trapped beneath layers of ice. It might have several overlapping layers of ice and water, as well as a possible global ocean between the ice layers. A unique characteristic of Ganymede is the presence of a tenuous oxygen atmosphere, produced when solar radiation and charged particles from Jupiter's magnetosphere strike the icy surface, splitting water molecules. Its low reflectivity suggests that its surface is probably composed of dark, colorless rock. Io, the innermost of the Galilean moons, is the most volcanically active body in the solar system, with over 400 active volcanoes continuously erupting sulfur and sulfur compounds, creating a multicolored surface dominated by yellows, reds, and blacks. This intense volcanic activity is fueled by heat generated by powerful tidal forces. Io orbits in a 1 to 2 to 4 gravitational resonance with Europa and Ganymede that keeps its orbit slightly eccentric, causing a tidal deformation that heats the moon's interior until it melts. The thermal energy generated is estimated at 10 trillion watts, about 25 times greater than all the energy used by humanity. Eruptions on Io can project material up to 500 kilometers or 310 miles above the surface, with volcanic plumes visible even from passing space probes. This material, mainly sulfur compounds and sulfur dioxide, falls back to the surface or escapes Io's gravity, feeding the plasma torus that surrounds the moon's orbit and contributing to Jupiter's magnetosphere. Due to Jupiter's gravitational attraction, Io experiences enormous tides in its solid surface that can reach up to 100 meters or 328 feet in height. These tides, in turn, generate enough heat for volcanic activity, giving Io its characteristic mottled yellow-orange appearance. Europa, the second Galilean moon, is one of the most promising places to search for extraterrestrial life in the solar system. Its icy surface, one of the smoothest in the solar system, presents a complex network of cracks and ridges, suggesting the presence of a liquid ocean underneath. This ocean, which is believed to contain more water than all of Earth's oceans combined, is kept liquid by tidal heat generated by the gravitational interaction with Jupiter and the other Galilean moons. Europa's surface is relatively young, with few craters, indicating active geological processes that continue to renew it. Detailed images also show chaotic regions where the surface ice seems to have broken and refrozen, perhaps due to convective currents in the underlying ocean or pockets of liquid water near the surface. The presence of a liquid ocean, combined with the energy provided by tidal forces, and possible essential chemical elements for life transported by comets or produced by chemical reactions, makes Europa a primary target for future astrobiology missions. NASA is currently developing the Europa Clipper mission, scheduled for launch in 2024, which will repeatedly fly over the Moon to study the composition of its surface and confirm the presence of the underlying ocean. Part of this liquid erupts from Europa's surface in geysers at the Moon's south pole. The prospects of finding life on Europa are particularly intriguing for astrobiologists. Europa's subsurface ocean meets all the fundamental requirements for life as we know it: liquid water, essential chemical elements, and a source of energy. The latter is provided by the tidal forces generated by Jupiter and the other Galilean moons, which keep Europa's interior warm despite its distance from the Sun. Some models suggest that Europa's ocean floor might host hydrothermal vents similar to those on Earth, where complex ecosystems thrive completely independent of sunlight. Moreover, recent observations of water vapor plumes erupting from the surface suggest that it might be possible to sample the underlying ocean without having to drill through the thick icy crust. These characteristics have led many scientists to consider Europa as the most promising candidate for hosting extraterrestrial life in our solar system, surpassing even Mars in terms of biological potential. Callisto, the outermost of the Galilean moons, is the third largest moon in the solar system after Ganymede and Titan, Saturn's satellite. Orbiting at a greater distance from Jupiter than the other Galilean moons, Callisto is not locked in the orbital resonances that cause the intense tidal heating of Io, Europa, and Ganymede. Consequently, it is geologically less active, with an ancient, heavily cratered surface that serves as a record of impacts in the inner solar system. The most notable crater is Valhalla, a concentric ring structure 600 kilometers or 373 miles in diameter. Despite its apparent geological inactivity, Callisto might also have a subsurface ocean, suggested by magnetic field measurements indicating the presence of an electrical conductor under the surface. The duration of a day on Jupiter is determined by how fast it rotates. Being the planet with the fastest rotation in our solar system, Jupiter completes a rotation every 10 hours or so. However, it's important to note that as Jupiter is a gas giant, it doesn't rotate as a solid sphere. Jupiter's equator rotates at a speed of 45,500 kilometers per hour, or 28,273 miles per hour, slightly faster than the polar regions. This causes a slight variation in the length of a day on Jupiter, depending on where you are on the planet. For example, at the equator, a day on Jupiter lasts 9 hours and 50 minutes, while around the polar regions, a day on Jupiter is 9 hours and 56 minutes. A surprising fact concerns Jupiter's role as a cosmic cleaner and planetary shield for the inner solar system. Thanks to its enormous mass and consequent strong gravitational attraction, Jupiter has the power to deflect or capture comets and asteroids that might otherwise head towards the inner planets, including Earth. In 1994, astronomers witnessed a spectacular example of this protective role when comet Shoemaker-Levy 9, already captured by Jupiter's orbit, fragmented into about 20 pieces and impacted the planet between July 16th and 22nd, creating enormous dark scars in the atmosphere visible for months. The impact generated explosions equivalent to millions of megatons of TNT, releasing energies that could have caused a mass extinction on Earth. Computer simulations suggest that without Jupiter's presence, the rate of catastrophic impacts on Earth would be 100 to 1,000 times higher, perhaps making the development of complex life impossible. Some astronomers hypothesize that the presence of a Jupiter in the outer zone of a planetary system might be one of the prerequisites for the development of life on rocky planets in the habitable zone, a true cosmic guardian. We should therefore be grateful to Jupiter for having protected Earth, as it is believed that the planet has played an important role in preventing asteroids from hitting us. As we've seen with the extinction of the dinosaurs, a single asteroid impact of catastrophic proportions could drastically change the course of evolution on Earth. Ultimately, without Jupiter's protective influence, life on Earth might not have developed as we know it today. One of the most fascinating aspects of Jupiter is related to its influence on dwarf planets beyond Neptune and on the overall structure of the solar system. Observations show that many objects in the Kuiper Belt have orbital periods that are integer multiples of Jupiter's, a phenomenon known as orbital resonance. This suggests that Jupiter has played a fundamental role in organizing the entire architecture of the outer solar system, moving planets and debris into specific regions of space during the formation of the system. Some models even suggest that in the first millions of years of the solar system, Jupiter migrated inward to the current orbit of Mars and then back outward in a movement called the Grand Tack, which would have completely reshaped the distribution of material in the protoplanetary disk. This model, known as the Nice model, suggests that initially the giant planets formed much closer to each other than they are today, with Neptune and Uranus in positions more internal than where we currently observe them. The gravitational interactions between these planets and an outer disk of planetesimals caused a gradual outward migration, which at some point became unstable. During this instability phase, which is estimated to have occurred about 700 million years after the formation of the solar system, potentially linking to the period of late heavy bombardment observed in lunar rocks, Jupiter would have moved slightly inward, while Saturn, Uranus, and Neptune would have moved outward, with the latter two possibly even exchanging their positions. The question we all ask at this point is, could there be life on Jupiter? Since Jupiter's atmosphere becomes warmer with depth, reaching a temperature similar to ambient temperature at an altitude where the atmospheric pressure is about 10 times greater than on Earth, scientists hypothesize that if life existed on Jupiter, it would be found at this level and would necessarily be airborne. However, these are just theories, as to date no form of life has been discovered on Jupiter. Although Jupiter itself might not be able to support life as we know it, some of its moons have oceans under their crust that could potentially host forms of life. Europa in particular, with its vast subsurface ocean kept liquid by tidal heat, is considered one of the most promising places in the solar system to search for life beyond Earth. This has led to the design of NASA's Europa Clipper mission, which will explore this moon to determine if it could host conditions suitable for life. If we look even further beyond the boundaries of our system, recent discoveries of exoplanets show us that planets similar to Jupiter are relatively common around other stars. However, many of these extrasolar Jupiters have orbital characteristics very different from ours. The so-called hot Jupiters orbit extremely close to their stars, completing an orbit in just a few Earth days. This contrasts sharply with the relatively distant position of our Jupiter, suggesting that planetary migration might be a common phenomena, but with highly variable outcomes. The particular configuration of our solar system, with the giant gas planets in the outer regions and the small rocky worlds in the inner ones, might be one of the elements that made the development of life on Earth possible. A fascinating curiosity is that if Jupiter had grown even more during the formation of the solar system, it could have become a star. In reality, it would have needed to accumulate about 75 to 80 times more mass than its current mass to trigger hydrogen fusion and become a star like the Sun. However, Jupiter already shows some primitive stellar characteristics. It emits more energy than it receives from the Sun, due to slow gravitational contraction and primordial heat trapped inside. This extra energy, about 67% more than that received from the Sun, is radiated mainly in the infrared. If observed in this wavelength, Jupiter glows faintly with its own light. Some scientists classify Jupiter as a sub-brown dwarf, a body halfway between a planet and a true brown dwarf star. In double or multiple stellar systems, objects similar to Jupiter but slightly more massive are common, orbiting around larger stars just as our gas giant orbits around the Sun. Ultimately, Jupiter continues to amaze and fascinate both professional astronomers and enthusiasts. With its storms that last for centuries, its complex system of moons that are worlds unto themselves, and its crucial role in the evolution of the solar system, The gas giant represents a natural laboratory for understanding the physical processes that dominate objects of this class. Missions such as the European JUICE probe, the Jupiter Icy Moons Explorer, will continue to study the planet and its moons, seeking to answer the many questions still open and inevitably discovering new mysteries. As we continue our journey through the solar system, keep in mind that every planet we encounter is not an isolated entity, but part of a complex system of interactions that extends for billions of years into the past and future. Jupiter, with its majestic presence, reminds us that even in the apparently static void of interplanetary space, dynamic and powerful forces are constantly at work, slowly but inexorably sculpting the destiny of our corner of the universe. In the next episode, we'll push even further from the Sun to explore the Lord of the Rings, Saturn, another giant with secrets all its own to reveal.